Okay, welcome to Chapter 8, Oxidation and Reduction. We'll learn the differences between these two processes and come to understand that they both occur in oxidation-reduction reactions. Both an oxidation and a reduction half reaction need to occur for the reaction to go forward. For this chapter, our learning objectives include being able to classify a particular change within a redox reaction as either the oxidation or the reduction part of the reaction. We'll identify an oxidation-reduction reaction. We'll identify the oxidizing agent and the reducing agent in a redox reaction and understand the difference between the agent term and then just the processes of oxidation and reduction. We'll be able to balance redox, and redox again just a shorthand notation for oxidation reduction or reduction oxidation equations. And then we'll identify and write the half reactions in an electrochemical cell. We'll also describe the reactions that occur when iron rusts. That's a particularly important reaction because it's a very common one in modern society. We'll explain why an explosive reaction is so energetic and why it occurs so quickly. We'll write equations for reactions in which oxygen is an oxidizing agent. And unfortunately, this would be something like a fire, a home fire, a business fire, right? Lots of oxygen in the atmosphere to act as oxidizing agent. We'll list some of the common oxidizing agents encountered in daily life. Obviously, oxygen's the major one, but we'll talk about some others. And we'll identify some common reducing agents. Finally, we'll write the overall equations for the metabolism of glucose and for photosynthesis. We'll use a balanced reaction to calculate the atom economy, if you remember that term from green chemistry, trying to keep the number of atoms in the reactants and desired product as economical as possible. And we'll look at the E factor of reactions. And finally, we'll describe the role of catalysts in minimizing waste in the chemical and allied industries, in particular by decreasing temperature and therefore decreasing all that waste heat that's a byproduct. So lots to do. Let's get right to it. Okay, so as we see here on this slide, we have burn and unburn. We don't usually think of unburning things, but because oxidation and reduction always occur together, something's burning and something else is unburning or getting reduced. So we have ammonium dichromate here on the left-hand side, and at the end, our products are chromium oxide, technically chromium 3 oxide, if you remember the naming conventions with that Roman numeral 3, because the chromium in the end product is a +3. The chromium in the starting material is a +6, as we'll get better at identifying once we learn how to balance these redox reactions. Nitrogen gas is another product, N2, and 4 moles of water for every mole of that ammonium dichromate starting material. So that ammonium dichromate was quite a violent reaction because it had both the oxidizing and reducing agents present right in that one material, and some things like the chromium got reduced and other species like the nitrogen got oxidized. So let's take a step back now and look at those terms. How are we going to differentiate between oxidation and reduction? Well, a simple way to look at oxidation is gaining oxygens, and therefore reduction would be losing oxygen. And that would be very, very important identifying characteristic when we get to organic chemistry. When we talk about things like combustion reactions, where hydrocarbons like natural gas or octane, which have carbon and hydrogen, when they burn in the presence of oxygen, the carbon now becomes carbon dioxide. So you're gaining oxygens in the carbon-containing compounds and losing them in the atmospheric oxygen. We could also think about following hydrogen instead. So oxidation, if it involves the gain of oxygen, it would commonly involve the loss of hydrogen, and therefore reduction would involve gaining hydrogen. So hydrogenation reactions are often also called reduction reactions. The simplest and best way to talk about oxidation and reduction has to do with electrons. So if you're losing electrons, that's oxidation. And if you're gaining electrons, that's reduction. And hopefully, if you've taken a prior chemistry course, even if it's been a while, you remember the acronym LEO, right? Loss of electrons is oxidation, And Leo says, grr, gain of electrons is reduction. So that's the most comprehensive definition of oxidation and reduction. And hopefully with that Leo says grr mnemonic, it's the easiest one to remember. Finally, increasing oxidation number is indicative of oxidation, and decreasing oxidation number is indicative of reduction. So we'll have to say a little more about that in our next slide. So here, first we'll talk about the mnemonic Leo. The lion says grr, goes grr, according to our textbook. And again, just as a reminder, Leo, loss of oxidation, loss of electrons is oxidation. Grr, gain of electrons is reduction. Here we see an example of a combustion reaction, one that most of us, those of us on natural gas anyway, do when we heat our home in the wintertime or cook with a natural gas stove. We take that methane, CH4, and burn it in the presence of oxygen. So 2O2, 2 moles of O2 from the atmosphere. And so for every mole of methane, CH4, that we burn, we end up with 1 mole of CO2 and 2 moles of H2O. So if we're looking, the carbon compound on the left-hand side, the methane itself, is 1 carbon atom bound to 4 hydrogen atoms, and the oxygen is just plain old diatomic oxygen, the oxygen, molecular oxygen that occurs in the atmosphere, at least for the most part. Ozone, O3, is in the upper atmosphere and sometimes gets generated down at our level, but mainly it's O2. If we look at the products, now that carbon-containing compound has no more hydrogen. It's been replaced by oxygens. So the carbon on the left has no oxygen atoms and 4 hydrogens. The carbon on the right has no hydrogens and 2 oxygen atoms. And then finally, the water, our other product, has 2 H2O. So on the left-hand side, the oxygen has no hydrogen. On the right-hand side, it has hydrogen. Now it's water. So if we look from left to right, the carbon compound, the methane going to CO2, well, that has lost hydrogen and gained oxygen. And those were 2 ways we said that we could follow an oxidation half reaction. For the oxygen, if you look, it hasn't really lost oxygen, right? Although it was 4 on the left, 2 of the O2, and now 2 H2O, just 2 on the right. So it's decreased the oxygen in that compound, although the oxygen has gone into the CO2 so that we don't lose any oxygen atoms overall. But in terms of that particular oxygen reactant and water product, we have indeed lost some oxygen and we have gained hydrogen, and those were 2 of the ways we could talk about reduction. So we can follow the oxidation and reduction half reactions by following the carbon-containing compounds and the oxygen going to water. Another way we can look at oxidizing and reducing processes is by looking at the agents. So oxidizing agents cause oxidation. That means they themselves are reduced. So if we look at that, remember the last slide, the oxygen was the oxidizing agent because it caused the methane to get oxidized, and it was reduced. It went from oxygen, molecular oxygen, to water. That was a reduction. It gained hydrogen. Reducing agents cause reduction by getting oxidized. So if we think of that previous slide, the methane was the reducing agent. It got oxidized to carbon dioxide. So the oxidizing agent causes oxidation by itself undergoing reduction. The reducing agent causes reduction by itself undergoing oxidation. If you can wrap your mind around that, then you're in pretty good shape for the rest of this chapter. Okay, so looking at an application of redox in modern materials, we can think of photochromic glass. This is very common in these eyeglasses that you may have seen with photochromic lenses. Those lenses have silver and copper 1 chloride embedded in the glass, and in normal indoor lighting they appear clear and colorless because there's not sufficient energy to cause the redox that causes the color. When you go outside, then the silver ions get reduced to silver metal, little nano particles of silver metal, and the copper 1 chloride gets oxidized to copper 2 chloride because we can't have a reduction without an oxidation. So the UV light's able to accomplish that, and the lenses themselves darken. And so here we see the reaction for that process. The UV light takes the silver ions and it adds electrons to them, causes photoreduction to silver metal, and we get those very small nano-sized clusters of the silver atoms that are numerous enough to cause that darkening effect. So now they look more like sunglass lenses instead of regular eyeglass lenses that they look like inside. So very versatile and a neat application of oxidation reduction reactions. Probably the most important redox application in modern society is electrochemical cells and batteries. So oxidation reduction reactions can be used to produce electrical energy, and we make use of this daily in our modern lives, and especially with respect to rechargeable batteries, lithium-ion rechargeables in particular. If we look at the reaction on this slide, we see copper metal dipped into a silver ion solution, so probably silver nitrate. Initially, the copper metal is that characteristic copper color. The silver ions are colorless in aqueous solution. After just a few moments, though, we see that we get silver metal depositing on the copper wire, and we get a blue tinge to the solution because when the silver deposits, silver ion reduces to silver metal, the copper metal oxidizes to copper ion. Those copper ions are what give that beautiful blue color that you're seeing appear as we move from A to B over a matter of just a few seconds. Ordinarily, we have the half reactions separated. So in the previous example, we saw the silver metal depositing on the copper wire. That's electroplating, but it's not really what tends to happen in electrochemical cells and batteries. So in a battery or an electrochemical cell, a battery is just multiple electrochemical cells hooked together. In a battery, or in one cell of a battery, we would have two electrodes. We'd have anode and cathode. So the electrodes themselves are typically pieces of metal or carbon, graphite, where electrons are transferred. So the anode would be the electrode where oxidation occurs, and the cathode would be the electrode where reduction occurs. And you can think about this in terms of some animals, if you like. We had our mnemonic there for Leo says Gur. Here you can think of anox, right? Anode is the site of oxidation, and a red cat. Reduction happens at the cathode. So hopefully that'll help you keep them straight, or you'll come up with your own more clever mnemonic device on your own. Okay, so when we talk about half reactions involve splitting up the chemistry into the oxidation process and the reduction process and treating them separately so that we can keep track of the electron flow. So in a typical example, like we saw with the silver depositing on the copper metal, the oxidation portion of that reaction was the copper metal, an element in its elemental state, like copper is metal here, has zero oxidation state, and as that process occurred, the copper ion was generated, right? So copper metal was oxidized to copper 2+ ion, so that's gone from a 0 oxidation state to a 2+ oxidation state, and as a result, it's released 2 electrons, right? So on the left-hand side, copper is neutral, 0. On the right-hand side, if we have the 2+ ion and then 2 electrons at a -1 each, we're also neutral overall, and that's important. The reduction half reaction would be the silver ion that was in that solution combining with an electron, or in this case, because we generated 2 electrons in the oxidation half reaction, we would need 2 electrons to be consumed in the reduction half reaction. That's why we have the coefficient of 2 in front of the silver ion, and therefore our electrons produced by oxidation equal the electrons consumed by reduction, and therefore we get 2 moles of silver metal reduced from silver ion for every 1 mole of copper ion oxidized from copper metal. When we sum these up, notice we have 2 electrons on the left-hand side of the reduction half reaction, 2 electrons on the right-hand side of the oxidation half reaction. They cancel and give an overall reaction of copper metal, copper solid, plus 2 silver plus 1 ions, aqueous, yield copper 2 plus ion aqueous plus 2 moles of silver solid. So the copper has undergone oxidation, and we can tell that because it lost electrons, right? Leo says Gur, so the oxidation should always have the electrons on the product side. The reduction, gain of electrons is reduction, therefore the reduction half reaction should always have the electrons on the left-hand side. And if we follow the oxidation states, copper goes from 0 to 2 plus, silver goes from +1 to 0. So in oxidation, the oxidation state goes up, becomes more positive. In reduction, the oxidation state goes down, becomes more negative. So in our example several slides ago now, we had the silver metal plating on the copper metal. And that's a good process if you want to silver plate something. But it doesn't make use of that flow of electrons. An electrochemical cell will separate those two half reactions so that we can make use of the electron flow, the electrical energy generated to power some device. In this example, you see the light bulb above there. So as the copper metal atoms are oxidized to copper 2 plus ions, the electrons that are released move from left to right and through whatever device we're using that electrical energy to power to end up on the silver metal electrode, where the silver ions from solution are reduced to silver metal. So it's important that we have that porous partition, because as the copper ions are generated, we need the nitrate ions, the counter ions of the silver nitrate solution, to be able to move over and charge balance. We can't generate a whole bunch of copper 2 plus cations without having some anions to provide charge balance. If we didn't have that porous partition, this process wouldn't be able to occur, because we wouldn't be able to keep overall charge neutrality. And again, the reason those nitrate ions can leave is because the silver ions are getting reduced to silver metal. So now we would be building up negative charge if we didn't have the nitrate ions migrating over to the production of copper ions on the left-hand side. Obviously, it wouldn't be a very good idea to have a bunch of tiny beakers inside of our batteries. So instead, we do what's called dry cell chemistry. So instead of having solutions, aqueous solutions of the reactant and product subspecies, we have this paste. So if you look at a typical battery, if you were able to safely cut it apart, don't do that. We don't have to do that because we have the picture right here. But what you'd find is the cathode is typically a graphite rod. So the graphite rod is what allows for the transfer of electrons. You've got a spacer, some sort of porous spacer there, as we see. There's the zinc case on the outside. That's your anode. That's the site of oxidation. So the zinc metal is going to become zinc ion, as we see in our overall reaction. And then you've got a moist paste of manganese 4 oxide, ammonium chloride, and some graphite powder. And that's what allows the manganese, which starts off on the left as manganese 4 plus, and turns out on the right to be manganese 3 plus. Okay, so the manganese is decreasing its oxidation state. It's gaining an electron per mole. The zinc is undergoing oxidation. It's losing 2 electrons per mole, and that's why we end up with the mole ratio. We have 1 zinc atom, or 1 mole of zinc atoms, reacts with 2 moles of manganese 4 oxide to give the zinc ion and manganese 3 oxide, plus some hydroxide on the product side and some water on the reactant side. That's why it's a moist paste. We do need a little water, but not a whole bunch of water like in our example with the beaker in the previous slide. So the previous example was a primary battery, or a single-use battery. What we tend to prefer are rechargeable batteries, right? Then we can have the processes go on and on and on in terms of charge-discharge cycles. It's less wasteful than having to dispose of batteries, again, safely. We don't just throw them in the regular garbage. You can bring them to places that collect batteries. The Broome County landfill, for instance, will collect them free of charge, and some area stores like Wegmans will take them. And so we certainly want to dispose of them correctly so they can have their materials reclaimed, but it's much better if we can get several hundred or thousand cycles out of our battery before that's necessary. Lead acid batteries, or lead storage batteries as they're often called, provide an example of rechargeable batteries. So if we look in the discharge discharge overall reaction, you have lead metal plus lead 4 oxide plus 2 moles of sulfuric acid give rise to 2 moles of lead sulfate, lead 2 sulfate now, and 2 moles of water. So that's why it's important that you have these batteries sealed so that the sulfuric acid inside doesn't leak. In the old days, they would be unsealed, and every so often you'd have to add water as the water evaporated, and you could accidentally expose yourself to the sulfuric acid, and therefore it was decided it's safer to just have them sealed so the water can't leak out and you don't have to risk exposure to add more water in. Notice on the left-hand side we have lead metal, which has an oxidation state of 0, and we have lead 4 oxide, which has an oxidation state on the lead of +4, and then both of those turn out to give lead sulfate as the product, and the lead sulfate has a charge of +2. So the lead metal got oxidized to the lead 2 and the lead 2 sulfate, and the lead 4 oxide got reduced to lead 2 and the lead 2 sulfate. So it's a neat little process. The recharge process is just the opposite. So discharge produces electrical energy by allowing that reaction to go. To recharge the cell, you'd have to put in an outside source of electrical energy to give 2 PbSO4, so everything's in the lead 2+ state, plus 2 moles of water, yields 1 mole of lead metal, plus 1 mole of lead 4 oxide, plus 2 moles of sulfuric acid. It's exactly the opposite of the discharge reaction, and that'll allow us to go through that cycle many, many times, and despite the environmental danger of lead, as long as it's sealed in a battery, a lead storage battery, and the battery's disposed of appropriately at the end of its life, there's typically a core charge on that battery so that you'll bring it back. Wherever you buy your new battery, they'll dispose of it, have it reclaimed successfully, and will keep that lead out of the environment. But they're very good batteries at what we tend to do in a car, where you're charging it a lot of the time whenever that alternator's on and working. Lead acid batteries are good at overcharging, being constantly charged and then only slightly discharging. They're actually very bad at cycling in what we call a deep cycle fashion. So if you leave your battery on, you forget to turn your lights off, and you completely drain the battery, likely you'll be able to jump start and recharge it. But if you do that a few times with a lead acid battery, you'll ruin the battery. It's not good at the full charge-discharge cycles. It's very good at discharging only a little bit and then getting charged quite a lot, like tends to happen in a vehicle. Lithium-ion batteries are much better at full deep cycle charge-discharge, and so they're obviously the battery of choice for any high-end application like laptops or cell phones. Alright, another type of rechargeable battery, nickel-cadmium batteries. They're not so commonly used anymore in things like portable radios and cordless devices because they do use cadmium anodes and nickel oxide cathodes, as you see on the slide, but they suffer from what's known as memory effect. So if you were to have a cordless drill, let's say, and it has a NiCad battery, and you charge it all the way up, and then you use it for just a little while, and you recharge it because your next project you think you're going to need to use a lot of it and you want it to have its full capacity. Well, the problem is it's probably only going to then discharge just a little bit because it remembers that last cycle. So if you don't completely drain it, if you only go, say, 25% of its capacity and then you recharge it, you're likely to only get around 25% discharge because that memory effect means that the NiCad battery has remembered its last cycle, and therefore you've damaged the battery, you've greatly reduced the capacity, and you've made it not so useful. And fortunately, nickel metal hydride and lithium ion, the more modern technologies or rechargeable batteries don't suffer very much at all from that memory effect. So they're definitely the way to go, and they're typically what's used now in devices that previously used NiCad batteries. So cordless drills, even cordless lawnmowers, and really high drain devices tend to be lithium-ion batteries. Fuel cells are another interesting electrical energy device. They're not technically a battery because there's really usually just the one cell, but if you think of a fuel cell, the fuel is oxidized at the anode, and the oxygen from the air is reduced at the cathode. And so the electrons are flowing through a wire to do work, but you're really able to go quite a while as long as you have a lot of that fuel to be oxidized. Sometimes the fuel can be a liquid. Methanol fuel cells exist, but oftentimes when we say fuel cell, we tend to think of the hydrogen fuel cell, where hydrogen is the fuel at the anode and oxygen is the oxidizing agent that gets reduced at the cathode. So your product there is water. It's very green, but it's actually tougher to accomplish than we initially thought. To get really pure hydrogen and to get that fuel cell to work well without getting poisoned has become quite a challenge. Okay, so when people say rust, typically they mean the rusting of iron, and it gives rise to that characteristic orangey yellow solid. So if we look at the process, it's the iron metal, which is present in wrought iron or steel or any of these high iron content materials. When that comes into contact with oxygen, which is always present in the atmosphere, as well as water, which is again always present to some extent in the atmosphere, you can get what's called iron 2 hydroxide. So the iron metal has oxidized to iron 2 ion. And then if we go even further, that iron 2 hydroxide can combine with more oxygen and more water to form iron 3 hydroxide. And that's what we tend to think of when we think of the rusting process. So the oxygen and the water we can't do much about. They're going to be present in the atmosphere in various amounts. What tends to really enhance this process and speed it all along is the presence of salts, in particular sodium chloride in our region, because that's the salt we spread on the road in the winter. And that's why we are one of the Rust Belt states, because we do add salt to the roads in the winter time to melt the ice, and that gives rise to our vehicles rusting much more extensively than vehicles driven in states that are not in the Rust Belt, states that don't add salt to their roads. So it's a consequence of living in the Northeast and enjoying these beautiful winters, is we do greatly enhance the process, the electrochemical rusting of iron. Now we see at the title here, corrosion, which is a more generic term for rusting, and it's really any metal theoretically rusts. Aluminum we often use in outdoor applications because aluminum's more reactive than iron. That doesn't sound right. Shouldn't we use a less active metal? Well, corrosion of aluminum is not a bad problem, because the aluminum is so reactive that it rusts right away, and the rust that it makes, aluminum oxide, is very tough. It's harder than the aluminum metal, and it prevents it from further corroding, any more oxidation. So when you cook on aluminum foil, you're really cooking on a thin transparent layer of aluminum oxide, and that's what lets the aluminum stay nice and shiny, because it's rusted in a thin layer that's harder than the metal itself. You don't get the problems with something like iron. When iron rusts, it makes that hydrated iron oxide, the iron 3 hydroxide that we saw in the previous slide. That's softer than the iron metal, so that flakes off and exposes more iron, and that newly exposed iron surface will rust, and then the whole process keeps going on and on. Well, with aluminum, because you rust quickly and because your corrosion product is stronger than the metal, it stays on there quite well and prevents further oxidation, further rusting. So aluminum's great for that, and it's used in a lot of outdoor applications for that reason. Titanium does something similar, but it's a little costlier. There's not as much of it in the earth, and it's also a little harder to work with. It's a much stronger material, but again, it will be a while before you see titanium applied. Wherever aluminum works, aluminum will stay. Okay, another problem you might have encountered in daily life is silver tarnish. And silver tarnish is the result of oxidation of silver, typically because of hydrogen sulfide, which is present in very small amounts in the air. It will leave that black film of silver sulfide, Ag2S, and this is really noticeable if you ever have put deviled eggs on a silver, or at least silver plated serving tray, because the eggs themselves have many sulfur compounds and release a hydrogen sulfide in particular, and that will interact with the silver. So hopefully you don't encounter that problem, and there's enough hydrogen sulfide in the air to tarnish even regular silver or silver plated objects without having to have the eggs there. The eggs will cause that process to happen much faster, and then you have products that will take off the silver tarnish. They're typically acids, things like nitric acid paste, that will remove that silver sulfide product and expose fresh silver, and you've got a little while before the whole thing starts over again. So here we see that process of cleaning your silver, so polishing the tarnished silver. Because most of the silver polishes do have acids, as I said, you're actually removing that top layer of silver now, and therefore eventually you're going to lose enough silver that if it's just a silver plated object, you're going to expose the bare metal pretty quickly. Another option, a better alternative, would be to let aluminum, which is again a very active metal, reduce the silver. So you'll have the aluminum take on that sulfide from the silver sulfide, and that will provide the same appearance, clean appearance, without actually removing much of the silver, because it's just taking away the sulfide ions to react with the aluminum and leaving behind the now reduced silver metal. Okay, so that's if you've never done that, it's safer than using these pastes, which often have relatively strong acids in them. You can just put the item with the tarnish on into a solution of sodium bicarbonate along with some aluminum foil, and watch and see how well you can clean that product. Okay, if we think about explosive reactions, explosions are also the result typically of redox reactions. If you think about a fire, a home fire, a business fire, fires seem to occur very quickly, and indeed in half an hour or so an entire structure can be consumed, but a fire is relatively slower than a chemical explosion, because in the case of a fire you need the oxygen from the atmosphere to be able to get in and permeate through and produce or at least continue the combustion reactions. So in the case of a chemical explosion, you have both the fuel and the oxidizing agent present right inside that one substance or that mixture of substances. So very rapidly, in fractions of a second at times, you can have an explosion, whereas a fire would require minutes to hours to accomplish the same extent of damage. So redox reactions that produce gases like nitrogen are often explosive. Even the airbag in your vehicle has sodium azide, which is a precursor to nitrogen gas that would be generated in the explosion that would inflate your airbag. The example the slide gives here from our text is ANFO, ammonium nitrate fuel oil. And if you look, you have 52 moles of ammonium nitrate, which is a solid, plus the fuel oil is a mixture of heavy hydrocarbons. Here we see just the C17H36 example, but that liquid fuel oil and the solid ammonium nitrate combine to react very quickly to produce 52 moles of nitrogen gas, 17 moles of carbon dioxide gas, and 122 moles of water vapor. So very fast, hot gases produced very quickly can do quite a bit of damage. Unfortunately, the attack on the Oklahoma City Federal Building in 1995 by Timothy McVeigh demonstrated just how damaging that ANFO mixture can be. Over 100 people killed and many hundreds injured, and many buildings in 20-block radius damaged or destroyed by that truck full of ANFO that McVeigh detonated in Oklahoma City back in 1995. Nowadays, it's a little tougher to get your hands on large quantities of ammonium nitrate than it was back before April of 1995, but it's still commonly used as a fertilizer, so farmers are permitted to have so much of it if they have so much land and can justify it, but it's more tightly regulated since now we understand just how devastating an explosion involving something like ammonium nitrate and fuel oil can be. Okay, so thinking about oxygen obviously a very special and important molecule to those of us aerobic organisms who need oxygen to live. It's the most common oxidizing agent, and it makes up about 20% of the air on Earth and about 50% of the Earth by mass, if you think about the amount that's as molecular oxygen in the air, and also all the oxides and other ways oxygen occurs in things like sulfates and other minerals in the crust. So lots and lots of oxygen containing compounds, and therefore about half of the Earth by mass is oxygen. In the atmosphere, it tends to be O2, right? Oxygen molecules as O2 that we breathe in and have brought to our cells. Ozone, O3, is not good for us. It can scar lung tissue, and it's very bad down here at the sea level. But up in the upper atmosphere, it's the ozone that protects us by scattering those ultraviolet rays and keeping us from getting sunburns so bad. Ozone, sometimes you'll notice it after a thunderstorm. It's generated down at the sea level by lightning bursts that can fuse O2 into O3. It has sort of a sweet smell. It's also noticeable around electric motors and things like that. So just be careful not to inhale too much ozone. Either oxygen or ozone will react with metals and nonmetals, forming oxides and making, again, all those different compounds that we find in the Earth's crust, as well as all of the things that occur when oxygen is used for aerobic respiration in humans and other animals. All right, so a little more on ozone. It's a powerful oxidizing agent, even more powerful than O2 itself. So that's why, as I said, it's harmful to humans. It's also harmful to plants and other animals because it's so reactive. But as mentioned earlier, in the stratosphere, it's very good for us. It's helping to protect us from the harmful ultraviolet radiation. So ozone's not all bad. It's just bad when it's down at our level, but it's very good for us up in the stratosphere. Hydrogen peroxide, H2O2, is another common oxidizing agent. And it's often used as a disinfectant. It will kill microorganisms pretty efficiently. It can be used to bleach hair or to bleach stains out of clothing or carpets. So it's pretty versatile. It's also an unusual exception to the normal oxidation state of oxygen, as we'll look at in some examples later on. Some other common oxidizing agents include potassium dichromate, K2Cr2O7. That was used in the early breathalyzers because it oxidizes alcohols and turns green when the chromium's reduced from a chromium +6 to a chromium +3. Nowadays, the breathalyzers typically use a fuel cell reaction, so you don't deal with the hazardous potassium dichromate that used to be necessary. Benzyl peroxide is an antiseptic, and it's used to treat acne. It's often in those creams that will be applied to the face to help with acne breakouts. Chlorine is a common disinfectant. It's often used in treating drinking water and wastewater to kill all the microorganisms. And bleaches, which are commonly either sodium hypochlorite or calcium hypochlorite or some combination of the two, are oxidizing agents used on fabrics to remove stains. So they'll remove the colors from the stains by removing the electrons through oxidation reduction. So the dyed molecule has its electron removed, and therefore it no longer appears colored. Well, we don't have so many reducing agents of interest, but if you are a metallurgist or interested in how we make metals, commonly it's done by using coke, which is a form of carbon, like graphite, only just a different variety. And it's produced by heating coal and driving off the volatile compounds, and you're left with this coke, this essentially pure carbon that you can add to smelt metals like tin. Here we see in this reaction where the tin ore oxide is combined with coke, and then the tin is reduced to tin metal, and the carbon from the coke is oxidized to carbon dioxide. Another way you could do this is to use aluminum, which is abundant on Earth, not as the metal, but as aluminum oxides or other forms of aluminum. And so once we use electrochemistry to make aluminum metal, we can use that reduced aluminum metal to reduce other metals, like chromium. In the case of the reaction we see here, the chromium 3 oxide is reduced in the presence of aluminum to give aluminum 3 oxide and chromium metal. So that's one way that we can reduce one metal oxide using metal, aluminum, instead of using coke, carbon, as we did above. For those of you who might be photographers and those who are still dealing in film, which is probably a very small number of people these days, black and white photographic paper has a silver bromide coating, and it's the silver ions that get photo reduced, as we saw before in the case of the photochromic glass lenses. For people who wear glasses that change to more like sunglasses outside, regular glasses inside, it's the same idea. The silver bromide in this case is exposed to light, and that will cause the silver ions to become silver metal when they're in the presence of this developer, hydroquinone. And the silver ions that don't get exposed are removed using sodium thiosulfate. So anything on the coating there that wasn't exposed gets removed, and you'll get a negative where the metallic silver is deposited. So that's how photographic processes and photography, at least film photography, relied on silver for many, many years. And so we just see another picture where you have the film there developed, and as we mentioned previously, it's the silver ions from the silver bromide that when they're exposed to light, they're reduced to the silver metal, which looks black in those tiny little particles of silver, and you get the negative image that you're used to seeing if you've ever seen film. Again, the younger folks out there may only be aware of digital photography and printing with inks to get your photos developed. But in the old days, we really did use developer, and it was a very interesting application of chemistry. In terms of human biology or biochemistry, we have some other important reducing agents out there. Antioxidants, those things that prevent other parts of the cell from getting oxidized, are just really good reducing agents. So they're typically present in foods or sometimes taken alone as a supplement. Examples would include vitamin C, ascorbic acid, tocopherol, vitamin E, or tocopherol, depending on how you like your pronunciations, and then vitamin A, or beta-carotene, really, which is provitamin A, would be examples of such antioxidants. So they get oxidized instead of the cell getting oxidized when you have these things like free radicals that are generated in the cell. They're looking for electrons. They can easily steal one from ascorbic acid instead of damaging potentially DNA or some other vital cellular component. They just take it from the vitamin C, which is happy to give it, and the antioxidant has prevented some cell damage there and done a good job of it. So antioxidants, they get oxidized easily and they prevent other things from getting oxidized. So they're good reducing agents since they are so good at getting oxidized. Hydrogen's another example of a great reducing agent, and it works for metals and nonmetals as well. So if you have a metal oxide like tungsten 6 oxide here, you can use hydrogen to reduce it to tungsten metal and water, so a fairly harmless byproduct. Hydrogen can also be added to unsaturated hydrocarbons, things that have double bonds, to saturate them. So that's where you get into these oils that are hydrogenated. They're how you make margarines, or artificial hydrogenated fats. That's not done so much anymore because we know the trans fats that they make are not good for us, so they don't do it as much as they used to, but still you can have hydrogenation of foods, unsaturated oils, to give rise to saturated, or at least less unsaturated products. Nickel or platinum is often used as a catalyst for hydrogenations because it seems to lower the activation energy by getting those reactant molecules in the right orientation. And when we say catalyst, again, a catalyst itself increases the rate of a chemical reaction by lowering the activation energy. It doesn't change the products, it just changes how quickly you get them. Alright, giving hydrogen a little more attention. Hydrogen's the most abundant element in the universe. It doesn't occur much on Earth as an element, but it's important for the compounds it occurs with, principally water, right? Oxygen and hydrogen combined in that H2O ratio give us probably the most common uncommon substance. It's very common on Earth, but uncommon anywhere else in the universe. Hydrogen can also be used to make ammonia and methanol, and to hydrogenate vegetable oils, as I said, to make margarines and shortening. So hydrogen does a lot of great chemistry once we can get the molecular hydrogen. And chemists have to typically look at water as the starting material to release hydrogen for these other applications. Another way you can make hydrogen gas is by reacting zinc with hydrochloric acid or other strong acids. So that's a nice way to displace the hydrogen from the acid, and you're left with zinc chloride in that example. Okay, and we see here that oxidation and reduction reactions are essential to life on Earth. Energy is obtained from food by oxidizing the food. And the example we show here is the oxidation of glucose, the only fuel that the brain can use. So C6H12O6 plus 6 moles of O2 for every mole of glucose gives rise to 6 moles of carbon dioxide plus 6 moles of water plus lots and lots of energy. And the way that we can capture that energy is by having this go through very, very small steps at a time. So rather than just burning it all at once, like if you were to throw glucose into a fire, we do it in controlled steps in our body so that we can capture the energy from each step. If you look at the reaction of photosynthesis, it's basically the reverse reaction of the oxidation of glucose. So green plants take carbon dioxide, 6 moles, plus 6 moles of water, plus energy, light energy from the sun, and they make glucose and other sugars as chemical storage species, and then they also produce oxygen, 6 moles of oxygen, as a byproduct. So that's why photosynthetic plants and blue-green algae in the oceans are very, very important to our survival on this planet, because they're the ones that are making the oxygen that then we can use to oxidize the glucose and other storage molecules when we're breaking it down for energy. And again, photosynthesis, we can't overstate how important it is, because it's the only natural process that produces elemental oxygen. And obviously that's essential for all of us animals on Earth that are aerobic respirators. We can produce oxygen by other processes, mainly breaking down water, right? Hydrolyzing water to make oxygen, and hydrogen, but that's relatively new that humans have had that technology, and it makes relatively small amounts of oxygen compared to all that oxygen generated through photosynthesis. So hopefully you've gained an appreciation for what a redox, oxidation reduction reaction is, and why it's so important, and hopefully you'll take a look at those example problems that are in the worked example problem folder on Blackboard to help understand how to better answer questions involving oxidation reduction reactions.